9A to C is just getting you to revise a couple things. What is a derivative? How do you do the derivative of a power rule? That's using power rules. Okay, so here we go. Couple of terms. Average rate of change. When you see average rate of change, what does that mean? It simply means to find the gradient between what? Can I please have Joe? What do you think? What's the average rate of change mean? Beautiful. Literally, it's just the gradient of 2 points. Okay, so when you find the average rate of change, it's another word to say find the gradient with 2 points. So you learnt that from year 9, y2 minus y1 over x2 minus x1. That's essentially what f of b minus f of a divided by b minus a is. Okay, that's just y2 minus y1, x2 minus x2. Yeah, x1. So, first exercise is just getting you to know the difference between average rate of change versus instantaneous rate of change. Instantaneous rate of change is the gradient at a single point on the curve. So if I drew a curve hypothetically like this, average rate of change is from this point to this point. How far did I change? What's the average change from horizontally? So x2 minus x1 versus how far have I grown vertically? y2 minus y1. That is average rate of change. Whereas instantaneous rate of change is talking about, well, right at this particular instant, what is the gradient of the tangent right at that point? And that's pretty much what calculus is about. It's about finding the gradient, or the derivative is to find the rate of change at one specific point, not two. Okay? So what you've done year 9 and 10, average rate of change, that's what that is. Instantaneous rate of change is what we're doing, or what we've done in year 11. All right, here we go. These are the notations. F dash of x means find the derivative or the gradient, instantaneous gradient at x equals a. Here's an example. Find the average rate of change of the function with rule f of x equals x squared minus 2x plus 5. So you've got a quadratic graph as x changes from 1 to 5. So here, let's work out, it starts at 1. So if I were to picture this, whatever this quadratic graph looks like, I'm just going to draw it randomly. We're saying from 1 to 5, find that gradient. So to find that gradient, we need at x equals 1, what's y1? Okay, so at 1, what's the y value? And that's why I wrote here f of 1. F of 1 just means sub 1 in, so 1 squared minus 2 times 1 plus 5. That gives me, what's 1 take away 2 plus 5 is 4. Is that right? Yes, it is 4. F of 5 is then 5 squared minus 2 times 5 plus 5. This works out to be 25 take away 10 plus 5. And that's really just 20. So now, if I think about the average rate of change, which is y2 minus y1 over x2 minus x1, that is literally just saying 20 take away 4 over 5 take away 1. So y2 minus y1 over x2 minus x1. Given that you know now this is 1, 4, and the other one is at 5, 20. That gives you now a total of 16 on 4. Average rate of change is 4 units. 4. That's the average rate gradient. If I asked you what is the instantaneous rate of change, then you'd have to find the derivative, but we're not going to do that yet. This is for the first exercise. So 9A looks at average rate of change, instantaneous rate of change. You also need to be okay with evaluating limits. Now, the limit of x plus h as h approaches 0 is written as lim of h approaches 0 of x. So limit of x plus h as h approaches 0 looks like this. If the denominator, so a couple of tips when you're solving or evaluating limits. If the denominator is not equal to 0, I think I did something wrong here. I think that's meant to say, if the denominator is equal to 0, factorize and simplify to solve. But then if the denominator is not equal to 0, I'm not sure what I meant by user there. I think I meant to say use substitution. Oh, it's probably just substitute. Might have done a typo there. Okay, so the question is, when you're looking at h approaching 0, if you substitute it in and it doesn't equal to 0, then you can just substitute it. If it does equal to 0, we know that we can't divide by 0, it's undefined, so hence you need to factorize and solve. So in the first example, if it approaches 0, it gets infinitely close to 0, but it's not exactly 0. But I know that that means this is a very small number. So if it was equal to 0, what would it approach to? Now at this point, if I sub h equals to 0 into that equation, the question is, will it be undefined? At this moment, it's not, so it's okay. So that's tip number 1. So here you get x squared minus 2. I don't think it was meant to be h to the power of x. It was meant to be hx. Fix that. So it should have been 0 times x and then plus 0 minus 6. Okay? Divided by 0 minus 3. And what we can see here is this cancels out. You end up with x squared minus 6 on negative 3. Which if you simplify that, I guess that's just negative 1/3 of x squared minus 6. So I guess what I'm saying there is, if h was infinitely small, then this, whatever function, this quadratic function, would tend closer towards 1/3 of x squared minus 6. Okay? Whereas in the second one, you can see there's a problem. What is the problem? If you sub h is 0, you now have 0 plus 2 squared minus 4 divided by 0. The problem is that's undefined. So you can't do that. So tip number 2, in that scenario, you're meant to factorize, simplify, and then you should be able to then solve from there. So here, instead of just doing a straight substitution, how do we simplify this now? You got h plus 2 squared minus 4. Anyone got a clue? What are you going to do? As h approaches 0, what would you do? All right. Let's try expand. You get h squared plus 4h plus 4 minus 4. All over h, conveniently, 4 take away 4 cancels out. You get h squared plus 4h on h. We've expanded, so what do we do now? How do we simplify? Very good. So you can think of it as factorizing the numerator. Whoops. H divided by h is 1. So that brings it down to h plus 4. Whilst you're doing this, make sure that you don't get rid of the limit. Because we're only simplifying the expression so far, so the limit should still be there. Okay, so then now, once you can substitute 0 in, we can see that as h gets infinitely small, it approaches something very small, plus 4, which you can then say equals 4. Okay? What about the next one? What's the limit of 3x minus 15 as h approaches 0? Very good. There's no h's in this case, so that means 3x minus 15 doesn't get affected. It approaches 3x minus 15. Okay, so that's just one of the exercises that you'll be working on in 9A. It's practicing to evaluate limits. Those are 3 different examples. One's substitution, one's factorize solve, or simplify, and the other one is check if there's any h variable that's affecting it. Okay? All right. Next bit. First principles. Can I get a show of hands who are confident from last year with first principles? How do you feel with first principles? Hands up if you know what first principles are. Do you guys know first principles? Kind of. Ooh, okay. It's not usually assessed, but I have seen it in the exams here and there. First principles, if you didn't know, this is the theory for instantaneous rate of change, which means to find the gradient at one point. So all the derivative rules that you learned from year 11 comes from this theory. All the proofs for all those rules come from first principles. Okay, instead of doing the first principles method, it takes too long to do. That's why you've memorized the rules. Maybe we'll get back to one of these points if we have a... Oh, we do have one. Here's an example. For those who don't know how to do first principles, here we go. Turn over to the next page. Example 2. Let's do this. So we're going to differentiate. Let's say you didn't know the derivative rules yet. We're going to differentiate using first principles. Here we go. First principle says... This is what the first principle says. Let's read it. Eyes and ears towards the board, thanks. First principles, if you don't realize, this is actually y2 minus y1. This is actually representing y2 minus y1. And if you do simplify it, you realize that x2 would be x plus h minus x1. That's why it ends up being just h on the bottom. Okay, so technically that is the gradient formula. So what I'm saying there is, if you had a graph, and this was x, and the next point was x plus h, then this would be x, and finding the y value would be f of whatever x is. So substituting x into the function will give me the y value. Same thing with the next one. This one would be x plus h, and then it will be f of x plus h. Because of that, if you want to find the gradient of those two, it would just be y2 minus y1. So y2 minus y1, which is the numerator here. And then x2 minus x1, it simplifies down to h. So really you're just finding the gradient, yeah? The difference is that you're trying to find the gradient of one point. So what we're saying is, what if h is infinitely small? Instead of it being this gap, x plus h is that little extra bit, what if it was infinitely close to the very first point? That's why, as this gets closer and closer to x, the gradient approaches the tangent at x. And that's called the instantaneous rate of change. Yeah, so that's what you're really doing. So to apply the formula, it means that you need f of x plus h, and you need f of x, and then you can simplify it. So here we go. Here's your formula. F of x is x squared plus 3x. So if you're trying to find f of x plus h, you're substituting x plus h in. So you get x plus h squared plus 3 times x plus h. Let's expand. Using expansion of perfect squares, by this point we should be able to do this quickly. So it should be 2xh plus h squared plus, expand the brackets over here, so that's 3x plus 3h. Collect any like terms that you can see. Looks like x squared is on its own. H squared is also on its own. But what we can do is we can probably take out the x's. So this is the x's. So x and an x. So if I took out x as a common factor, then I'll have 2h plus 3. And the last one is plus 3h. So far, so good. So I can see as a quadratic, that is the x squared, that's the x, and that must be the constant. Cool? Next one, f of x, on the other hand, f of x is x squared plus 3x. So from here, now we're saying take f of x plus h, take away f of x. So if I do that now, let's write it out. Limit of h approaches 0. We're taking f of x plus h, which is up here, and we're taking away f of x. So just by inspection, you can already see x squared minus x squared is going to cancel out. You're going to minus the x's with each other, which maybe I should have just kept it in the expanded form, because 3x take away 3x would cancel out. That means you still have 2xh left over. You still have plus h squared left over, and you still have plus 3h. Now, if that was too fast, I'll just do the intermediate steps so you can see. I just did x squared plus 2xh plus h squared plus 3x plus 3h, take away x squared, take away 3x. All over h. Okay, so all I was just doing is this is your f of x, and this is your expanded version of x plus h. So far, so good? So if I simplify this now, we can see evaluating limits. Just did this to get there. Evaluating limits, if you sub-zero into the h, it's not going to work. It's going to be undefined, so simplify where you can. Conveniently, h can cancel out, and you end up with 2x plus h plus 3. Limit, don't forget the limit because we haven't used it yet. What would that approach to? 2x plus h plus 3, if h approaches 0, the function approaches 2x plus 3, very good. And that is how you would have done it if you learned power rule from last year. Derivative 2x, what's derivative 2x again? Very good. This is 2x here, and the derivative of 3x is positive 3. We'll get onto that if you've forgotten the power rule. Remember how you drop down the power minus the power by 1? That's how I got 2x to the power 1. This one's 2 powers 1. Drop it down, and then minus it by 1, and that's how you get plus 3. These two answers are the same. So power rule is just a shortcut instead of doing first principles. But you do need to know how you do first principles. Okay? You don't do that all the time. All right. Last bits for today's notes to revise for what you need to remember. Power rule. So the one that I just gave to you just now, x squared plus 3x. This is called the power rule. If you have a polynomial function, which we do over there, it's x squared. The derivative is n times a times x to the power of n minus 1. Okay, so essentially it's what you learned from last year. Bring down the n and then minus the power by 1. That's why for x squared, if you bring down the power, it's 2 times x, power of 2 minus 1. That's how I got 2x. Same thing with this one. Bring down the power, it'll be 1 times the 3 times x to the power of 1 minus 1. That's how I ended up with the 3. You guys ready for some year 12 examples? So, unlike last year, you would have got a bit easier versions of this. I've just combined the ones that students tend to make a mistake with. Example 3. Huh? Oh, that's right. We did a quiz. That's why it took so long. All right, team. I guess I'm going to pause the video there and we'll continue from 9C onwards. I'll give you the worksheet next week. Next lesson.